Hello, we are back for lesson 4.3. We're going to be learning about logarithmic functions. They are the inverse function of an exponential function. So I want to show you what I have up on Desmos under the link that I provided in Canvas. This is the green function here, y equals a to the x, or exponential function. And I can change the slider so I can look at a's between 0 and 1. Remember, we can't have a negative a. And we can't have 1, but we can jump, and then it goes to begin increasing exponential function. And then what's cool is if I click up here on a log function in red, you can see it's an inverse function, and it's always an inverse function is always symmetric around the equation, linear equation y equals x. So you can see that's in purple there. So pretty cool. So I wanted you to see that. So as I change a, look at what happens to the functions. Isn't that so cool? And we can really zoom out to get a good picture of. So the log function is in red. It has a natural asymptote at x equal to 0, and then goes to infinity as x goes to infinity. So that here is shows our definition of logarithm on our beginning of 4.3. And what's cool is this is how I always thought about interpreting logarithms for myself, but I like how they did this here in the book. So if we turn to page 346, it says, we read this as log base 3. So the little subscript there is a 3, that's your base. So it says log base 3 of 9 equals 2. And so how we would say this to ourselves, and this is exactly what I used to do. I love this book. It says, to what power must 3 be raised to produce 9? The answer is 2. And that's all written here. So you take 3 and you bump up 2 into the exponent, and that equals 9. The next one says log base 5 of a square root of 5 equals 1/2. So it says, note that square root of a number is the same as raising a number to the half power. To what power must 5 be raised to produce the square root of 5? And that would be 1/2. Then we have the log base 3 of 1/4 equals a negative 2. To what power must log base 2 of 1/4 equals a negative 2. So what power must 2 be raised to produce 1/4? And the answer is a negative 2, because a negative exponent puts the exponent in the denominator. And then we just have a general one here. Log base a of b equals k. So a has to just be greater than 0 and not equal to 1. To what power must a be raised to produce b? So let's look at some in our book here. I'm going to go to my paper. Let me bring this up here. So I'd like us to look at number 11 on page 346. And I made, actually it's on page 355. This is on page 355, number 11. I made a little table for myself, just like they have in the book, so that you could see. So we're going to take the logarithmic form and write it in the exponential statement form. So this says log base 3 of 1 equals 0. And so this is written as 3 to the 0 equals 1. So I think of it as my base on my log becomes the base in the exponent and bumps this 0 to the exponent equal to 1. So it kind of makes like a little circle. So the next one, when you don't see a base, we assume that it's a base 10, kind of like our money system, base 10. So this is 10 to the 1 equals 10. And then this one is log base 5 of 1/5 equals a -1. So that's 5 to the -1 equals 1/5. And then log base A of B, I'm sorry, log base A of X equals B. So A to the B equals X. So this is going from logarithmic to exponential. They're inverse functions of each other. Let's look at 13. I have a bunch I'd love to look at today just so you can experience these new functions. So now we're going to go from the exponential statement to the logarithmic statement. So we're taking the log of base 3, log base 3 of 81 equals 4. The next one is log, and the base, when we use the word base, we're talking about the same thing. So base and exponent is going to be your base and your log. And then 5 to gives me 1/3, right? So this is going to be 1/3 here, and then this is going to be, I put these in parentheses, the third root of 5. And then this one is log base 6 of 1/6 equals a -1. And then log base A of U equals U. It's hard to read what the letter is in the book. I think that's U. A to the U. I think this might be a V here. Let's look in the book. Oh, the letter is so little in the book, I can't even read it. I thought I had it. It's right here. Let's just zoom in. That is a V. It's a V. A to the V equals U. I'm glad to know that. Okay. So let's go back to my paper here. Okay, so this is a V. So log base A of U equals V. That's more like it. Okay, the next ones I'd like to look at is 15, 17, and 19. So 15, 17, and 19. So it's asking us in this section to evaluate each expression without using a calculator. So this is log, and it doesn't have a base, so that's base 10, log of 10,000. So this is really base 10, we just don't see it. So this is 10 to the what equals 10,000. And that would be X to the 1, 2, 3, 4. X to the 4th will equal 10,000. So 10 to the 4th will equal 10,000. So X is going to equal 4. So number 17 says log I think this is the cubed root of 10. And so, again, this is base 10 because we don't see it. So 10 to what exponent will give me the cubed root of 10? So that means x must be 1/3, because the fractional exponents are really the same as a root. So let's look at number 19. So number 19 says, ooh, this is a new one, ln e squared. Natural log. So this ln is considered the natural log because it's the inverse of the natural number e when we talk about exponents. Remember we did that. We used the natural number e in the lesson 4.2. So this is really a base e, okay? So this is saying e to what x value will give me e squared. So that means x just needs to equal 2. So 25 log 10 to the k. So again, we're assuming it's base 10 because we don't see a base. So this is 10 to what x will give me 10 to the k. And so that means that x just needs to equal k. (27) and 30. So 27 and 30. So 27 is the log base 2 of square root of 2. So that means 2 to what x will give me the square root of 2. And remember, the square root of 2 is equal to 2 to the 1/2. So that means x just must equal 1/2. And then 30 is log base 7 of 1/49. So this is saying 7 to what x will give me 1/49. And I know that 49 is 7 squared, so this is really 1/7 squared. And I know that when my square is in the denominator, it's really 7 to the -2 in the numerator. So now I can make the connection that x must be equal to a -2. These are fun to think about and look at. So now I'd like to look at the grouping of 35 and 38. And 38. This grouping says evaluate the expression to 4 decimal places using your calculator. Okay, so 35, we're going to look at 2 log of 4, and 38, we're going to just put both of these in decimals. 38 is the natural log of pi. So we'll look at those. And then we're going to come back and learn about something else here in a moment. Let's go to decimals. Number 35. And we're going to put in 2. And then you can go to functions down on your keyboard. So functions. And you kind of just have to scroll through down, 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 and you'll see the calculus ones. We're going to do the natural log in a minute, but we're going to look at log first. So 2 log, and then 4 goes into the parentheses, and that comes out to be approximation of 1.204. And then the other one we wanted to look at was number 38. And that's the natural log, and then we have to find the pi symbol. So let's go find that here. Down in our menu. And it's down in our menu, right down here by the square root. We're going to click on pi. And it looks like the natural log of pi is equal to approximation of 1.1447. And it said round answers to 4 decimal places. So 35 should have been 1.2041. So the next grouping of problems I would like to look at are 43 and 45. And they are all about the change of base formula. So if we go to the book, we can look at, excuse me, it's on the page 349 in our book, and it's called the change of base formula. So it allows us to change bases. So it says, because your scientific or graphing calculator has special keys for only common logarithms, that would be log base 10, and natural logarithms, which is the ln base e, you must use the change of base formula to calculate logarithms with respect to other bases. So to write a logarithm with base a in terms of a logarithm with base 10 or base e, we use the following formulas. So if you want to do log base a of x, then you can put it in base 10 by taking the log 10 of x over the log 10 of a. So you just use both base 10s, and then you do of x and of a. Or you can do the same thing with the natural log. So you can see here they did that in example 7, log base 6 of 15. So they said, okay, we're going to do the log base 10 of 15 over the log base 10 of 6. That's where the 15 is over the 6, but you're using log base 10 in your calculator to get 1.511. And we can do that same one in our calculator. The cool thing is Desmos will let you do a different base. So if you go to functions and you go all the way down to the log function, oops. Sorry, I meant to do the log base a. They have a log base a, so they've already done it for you. So I'm just going to show you the log base a. The one in the book was log base 6 of 15. So we can actually do log base 6 of 15. But then I can show you how you would use log base 10 to do the same thing. So if you do log of 15, oops, and then we're going to divide by log of 6, it knows to use base 10. So you can see that you can use the change of base formula. Oops, I want to undo that. You can use the change of base formula to do the same thing. Change of base formula. But because we don't even need the change of base formula, we can just use the log base a formula in Desmos, which is nice that it does that. But let's just go to my paper for a moment, because 43 and 45 are asking us to use the change of base formula. So let's just set it up so we understand how it works. Because it's going to help us when we go to do some solving. So 43 says log base 3 of 1.25. And then I'm going to write down 45 as well. Log base 5 of 0.5. So we're going to set both of these up and check them out here. So the change of base formula would say, okay, we're going to do log base 10 of 1.25 over log base 10 of 3. And that would give us the same answer. And I'm going to show you that here. So log of 1.25 divided by the log of 3. And we get 0.2031. And you go to math and numbers. I think it's down here. No, it doesn't do the math. Oh, so if you go to math tab and then arrow up, it takes you to the bottom and it's the log base formula. So if you do the log base formula, it allows you to put base 3 there and then do 1.25 and enter, and you get the same answer. Okay, so let's try number 45 is going to be log base 10 of 0.5 and log of 10 of 5. And like I said, you can either use this or you can use your log base formula and that's most of your graphing calculator. Now I'm going to go ahead and just copy this and edit because it's a lot easier. Oops. It's 0.5 and delete that. And that comes out to be a negative 0.4307 to 4 decimals. And remember, when you don't see a base, it's because it's assuming base 10. So let's look at number 52 and 54 in the book. So this section says, use the definitions of logarithm to solve for x. So 52, let's just write these down. 52 is log base 5 the square root of 5. So this means 5 to what x gives me the square root of 5. And we actually did this one on the last page at the beginning. 5 to the x gives me 5 to the 1/2. And because now we have like bases, we know the exponents must equal each other, which is 1/2. 54 says log base 6 of x equals a negative 2. Log base 6 of x equals a negative 2. So this says 6 to the negative 2 equals x. And 6 to the negative 2 means 1 over 6 to the positive 2. Because a negative 2 means it's in the denominator. So it's 1 over 36 equals x. Okay. Okay, then I would like to look at 59 and 61. So 59. So this section says, find the domain of each function. Use your answer to graph the function and label all asymptotes and intercepts. Well, we've been getting really good at asymptotes and intercepts in the last couple chapters. So 59 says 4 times the log base 3 of x. 61, I'm just going to jot it down on here, is x equals log of x minus 3. And this was an f of x function. Okay, so let's just go through some things that we know from previous chapters, just to kind of like wrap our brains around this. So this 4 here means that we're doing a stretch of 4 after we take the function. And this log base 3 of x function is really 4. And this is the same as this part here is 3 to the what equals x, right? So it's kind of like 3 to the y equals x. So we're kind of doing the inverse function of that. So it's a 4 stretch. So let's go to Desmos and just see what we can play around with here. So if we said log base 3 of x, we're saying, what can I raise 3 to get x? So we're kind of, I like to think of these in the inverse here. So what could I raise 3 to get to x? So if I wanted x to be 0, I could never do that, right? Because there's no exponent of 3 that could get me 0. So I could never have x to be 0. So there's no y-intercept, right? Because the y-intercept is our asymptote. We talked about that at x equals 0, okay? No y-intercept. Okay. And then what x value will this be 0? So that means when I raise 3 to the 0, I get x. So that would have to be a 1 because 3 to my function y. So 3 to the 0 equals 1. And that's x, and that's y. So my y-intercept, my x-intercept, let's just rewrite that, my x-intercept is at 1, 0. Okay, but then we're multiplying by 4 afterward, but y is 0, so it doesn't really matter, right, on that one. So let's just go and put this into Desmos so that we can get familiar. Make a little note here for us. This is number 61, and we're going to just put in y equals 4 log of, oh, we need the log base. So let's go to functions, find that log base, and it's log base 3 of x. Okay, I'm going to go up and turn my other function off up here since we're no longer looking at it. Okay, so here's a new function we're looking at, and I'm going to click on it, and I'm going to go to the gear and just look at the table and look. So it's undefined for negative numbers, so I'm just going to delete those. I'm going to put some bigger numbers than 1. So I'm going to put in a smaller number between 0 and 1, 0.2, 0. Or 0.4, 0.3, 0.5. Let's just see. Okay, so very negative. We can see that here, and then it's going to grow. And sure enough, there's 1, 0. That's our intercept. And that's what they wanted. They wanted us to be able to graph the function and label asymptotes and intercepts. There we go. So the other one is, oh, that was actually number 56. 9. So we're going to do 61 down below. Okay, so 61 is y equals, and it's, oops, log, natural log of x minus 3. Okay, so oh, we gotta turn this other graph off. So this one is just our natural log of x, right? And then we're going to subtract 3. So we're going to shift it down 3 is all we're doing. So this is cool because when will it cross the x-axis? That is it's going to be a long, long while before that happens. So let's just click on it and make the table here. So our so when x equals 1, we're at a -3, and then it let's put in 100 and see if we've crossed the x-axis yet. Oh, we're at a -1. Let's see if we put, it took us from 1 to 100 on x to go from a -3 to -1. So let's put in 1000. Oh, we're at 0. Oh, I got lucky. I got lucky. I found the y-intercept, the x-intercept. So that's pretty cool. There's our x-intercept. Is at 1000, 0. Okay. And it looks like we still have our asymptote at x equals 0, and there's no y-intercept. We already talked about that. So I am going to just take you back to my paper here so we can just see how I jotted all this down. And how could I find that x-intercept? So if we said that our g of x is just equal to y, and this is log base 10 of x minus 3, and I wanted to solve for x, for the x-intercept, right? So y is 0. So we have to isolate this log thing. So if we add 3 to both sides, well, that's interesting, because now we have an exponential setup, right? We can take this log statement and put it to an exponential statement because these equal each other. So this is really base 10, right? So 10 to the third equals x. So x equals 1000. So one of the probably the easiest x-intercepts to find. Pretty cool. Okay, so the last couple problems I'd like to look at are 84 and 86. In your book. So 84 and 86. Because you're probably wondering, what in the heck do we use logarithms for anyway? Well, we use them for earthquakes and calculating their magnitude, because they're all base 10. So let's just go here. So they actually discuss it here on the bottom of page 352 and the top of page 353. It's earthquakes are measured on something called the Richter scale. And the Richter scale is using a logarithm of a ratio of I compared to I0, where I represents the actual intensity of the earthquake and I0 is a baseline intensity used for the comparison. So that you can always be comparing whenever they say it's a recording of a 7 on the Richter scale, they know what that ratio is. Okay. So for examples, it says a recording of 7, for example, corresponds to an intensity that is 10 times as large as the intensity of an earthquake with a recording of 6. A says, if the intensity of an earthquake is 100 times the baseline I0, what is the magnitude on the Richter scale? Okay, so that means if it's 100 times I0, then it must be the log of 100 because the I0s cancel. And that would be 10 to the what gives me 100, which is 2. So that would be a base 2, a 2 magnitude on the Richter scale. And then B says, a 2003 earthquake in San Simeon, California registered 6.5 on the Richter scale. Express its intensity in terms of I0. So we know that the Richter scale is 6.5. And we're just saying, we don't know what I0 is, but it's the base value. And so we're going to say, we know base 10 to the 6.5 equals this ratio. And so we know that I equals 10 to the 6.5 times the initial intensity. So let's do a couple of our own. Actually, let's, I'd like to look at number 84. So I'm just going to take you there in the book here so you can read it. We can read it together, 84. So using our formula for the magnitude, which is R of I, the magnitude is equal to the log base 10 of I over I0. And 84 says, if the intensity of an earthquake is 1,000,000 times the baseline, so 1,000,000 times the baseline intensity I0, what is its magnitude on the Richter scale? Okay. So I'm going to put my paper here. So 1,000,000 times the baseline would be R0, R of I is equal to 1,000,000 times the baseline. We have to take the log of that. 1,000,000 times the baseline I0 over I0. So that means the magnitude is equal to the log base 10. The I0s cancel. So it's log base 10 of 1,000,000. So that means 10 to what exponent will give me 1,000,000? And that is 10 to the 6. So x must equal 6. So it's a 6 on the Richter scale. Magnitude is 6. So let's look at number 86. Number 86 says, in 1984, another significant earthquake in San Francisco registered 6.1 on the Richter scale. Express its intensity in terms of I0. I0. Okay, so 6.1 is equal to the log of something, right? The ratio of I over I0. And they want us to find, express its intensity in terms of I0. Okay, so we know that 10 to the 6.1 equals I over I0. And so if we want to solve for its intensity, we can say 10 to the 6.1 times I0. And 10 to the 6.1 is going to be a little bit bigger than 1,000,000. So let's just do 10 to the 6.1. And it is, write it. So it is 1,258,925.412 times the initial, the base intensity. Pretty cool. Pretty cool. So you're going to have a little assignment, and that is there have been a lot of interesting earthquakes in getting more frequent and stronger. So I'd like you to find one. You can search different, current earthquakes. And I'd like you to find, I'm going to have a little assignment that I want you to do in Canvas. You'll find that assignment there. So catch me back for lesson 4.4.